This is Nuclear Chem Video 1. So, nuclear chemistry. How is nuclear different than all the chemical reactions we've been talking about all year? Well, nuclear reactions involve changes in the nucleus because it's nuclear chemistry. So, transmutation reactions, which are going to be nuclear reactions, are when we take an element and we make a new element. So, for example, all year, let's say you were balancing a reaction. You had one sodium on one side and you had one sodium on the other. We had to make sure we have the same amount of atoms on each side. Here, it's like taking one element, U, and then coming up with a completely new element. So we're changing from one element to a completely different element. We're transmutating because we're changing the nucleus or the number of protons. Remember, when you change the protons, you change the identity of the element. In these nuclear reactions, we're going to emit particles. So radiation is a broad term for any energy or particle that's emitted that travels through space. It could be typically in the form of a wave. So you're not going to be able to see these radioactive particles. So nuclear reactions produce high energy radiation waves or high energy particles. The reason they're releasing these particles is because the isotopes are unstable. So the ratio of protons to neutrons, if they're the same, meaning that if you have the same number of protons and neutrons, for example in carbon-12, 6 protons, 6 neutrons, then you're going to be stable. So if we look at this picture over here, it's showing you something called the belt of stability. So it's able to predict when the numbers are the same, like here, let's say 10 protons and 10 neutrons, you're stable and you fall on the belt. We could actually figure out what kind of radioactive particles are going to be emitted from elements that have unstable nuclei. But in general, what you could say is that an element with an atomic number larger than 83 will be unstable. And if you're unstable, you're going to be radioactive. So any unstable nucleus is radioactive. And the reason that it's unstable is because of the proton to neutron ratio. So just recall, remember what we're talking about here with isotopes, same protons, different neutrons. These are 3 isotopes of hydrogen, deuterium, and tritium. They all have 1 proton, same atomic number, different numbers of neutrons, causing them to have a different mass. So when those ratios are off, that's when it's going to be unstable and be radioactive. So now what we need to do is we need to look at reference table O. So I need you to take out your reference table and look at the types of particles that we can emit: alpha particles, beta particles, gamma particles. We also need to be able to discuss their penetrating power. So on the chart, alpha, if you look at the mass, is 4, charge is 2. So the top number is the mass, bottom is the charge, just as we've been talking about all year. Beta particle mass is 0, charge is -1. Gamma, no mass, no charge. As far as being able to penetrate through substances, alphas are the weakest, gammas are the greatest. I remember GG, gamma is the greatest. So alpha weakest, gamma greatest. When we pass them through, or we want to know where are they going to deflect when we pass them through a magnetic field, let's look at the charge. Gammas have no charge, so when we're passing them through a magnetic field, are not going to be attracted to a positive or a negative plate, go straight through. Beta particles have a -1 charge. We pass them through a plate. Where are beta particles going to go? Opposites attract towards a positive plate. Let's look at the alpha particles. Their charge is 2. They have 2 protons, basically a helium nucleus. Pass them through a magnetic field. Where's the positive going to go? Boom, towards the negative. You don't have to memorize any of this. Obviously, it's all listed on table O. You do have to be comfortable with the symbols. So the symbols are here. The notation for how we write them. Alpha particles, you could write 4/2 He or over 4/2 with this alpha. Do not put fraction signs. These are not fractions. The top number is the mass. The bottom number is the charge. Here's just another representation showing you beta particles are negative, would be attracted to a positive plate. Gamma rays, straight through, no mass, no charge, no attraction. Alpha particles are positive, would be attracted to negative. All right, let's go each particle by particle emission. Here's a reaction. Let's look at the products. What do you got? 4/2 He. What is that? That's a helium nucleus. What do we call that? Let's go back to our chart. 4/2 He is an alpha particle. So what we're looking at here in this reaction is an alpha emission. We are looking at a reaction that produces an alpha particle. What happens? Well, let's look at the mass. The mass on the left is 226. That means the mass on the right has to be 226. So 222 plus 4 is going to add up to 226. Conservation of mass. Let's look at the charge. Charge on the left is 88. Charge on the right has to be 88. 86 plus 2 equals 88. So even in nuclear reactions, conservation of charge, mass, and energy. What happened when the alpha particle was released? Well, the mass started out as 226. It went to 222. So what happened to the mass? It went down by 4. What happened to the charge? It started out as 88. What happened to the charge now? It's 86. Look, new element, Ra, Rn. This is a transmutation reaction. Nuclear reactions are going to make new elements, new identity of the element. I can't be 88 and be one element, 86 and be the same element. The element has changed. We should know that alpha particles are the heaviest. So if you look at all these different types of particles that you can release in a reaction, alphas have the biggest mass. Next up are beta emission. Beta emission just means that on the product side, you have a beta particle. How are you supposed to know 0 and -1 is beta particle? You haven't learned it yet. You're just supposed to learn it now. That's how you're supposed to know. Okay. So beta particle, you come here, look at the chart, 0 - 1 E. So table O is going to help you figure out what type of emission you have. You look at the product side of the reaction, whatever particle is there, you go up to table O and you look up what the particle is. There's a beta particle. As we did in the alpha particle emissions, basically what you're looking at is make sure that the mass on the left and right are the same, make sure the charge on the left and right are the same. So if you look at the left here, the mass is 214. The mass is over here 214 already, so the beta particle is 0 because 214 and 0 equals 214. 82, that means the mass over here has to be 82, so 83 - 1 equals 82. We also have gamma emission where you release a gamma particle, and positron emission where you release a positron, which is basically just a positive electron. So in general, any of these reactions where we're going to release an alpha, beta, positron, or gamma radiation, we need to make sure that we're balanced in terms of mass and charge. The sum of the masses, the top numbers, must be the same on each side. So if I have a mass of 12 on the left, I need a mass of 12 on the right. Same thing with atomic numbers. Whatever the atomic numbers are on the left, the sum of them, the sum has to be the same on the right. So here's an example. The mass on the left is 9 + 1 is 10. The mass on the right has to be 10 as well. So see how the blue numbers are going to add up to the same number. The bottom, the charges are atomic numbers. 1 + 4 is 5. On the right, 3 + 2 is 5. Okay, so lastly, we're going to have to be able to figure out what an unknown is given an equation. So for example, you can go through each of these to see if they make sense. I'm going to go through the top one with you. You'll have an identified element where the underline is X, and you have to figure out what X should be. So if you look at the reactant side, the reactant has a 53. The product has a 54. We need them to be the same. So that means that this bottom is going to have to be a -1 to make the right side be the same as the left side. The top on the mass on the reactant side is 131. The mass on the product side is 131. So I don't need any mass, so my mass is going to be 0. Then you go to reference table O, and you look at what has a -1 on the bottom and a 0 on top. -1 on the bottom, 0 on top. Boom, beta particle. What are you supposed to write next to it, an E or a B? So you can write whatever you want. I just wrote E. All right, one more. You have B, an example B. The mass on the left is 239. The mass on the right is 235. That means you need a 4 on top because 4 + 235 equals 239. You need the mass on the left to equal the mass on the right. On the reactant side, the charge is 94. On the product side, the charge is 92. So that means I need a 2 to get the mass to be the same. Go to table O. What does that mean? So look for a 2 on the bottom, a 4 on the top. There we go. Boom. Alpha particle. What do you write? HE, or kind of like a weird scripty A. We're just going to write HE. Look at the last two examples. Make sure that they make sense. And finally, transmutation reactions. There are two types of reactions. One is called natural transmutation. One's called artificial transmutation. All you need to know is that natural transmutation happens on its own, so there'll be one reactant. And artificial transmutation requires another reactant. It's like fake. So it needs something to be bombarded into it to make it happen. So if you look, here's an example of natural transmutation, one reactant. Here's artificial transmutation, two reactants in each case. We'll go over examples of transmutation in class, but right now that's all you have to know. One reactant natural, two reactants, or more artificial. Done.